Welcome to this lesson on using differentiation to master stationary points. By the end of this video, you will be able to find the coordinates of stationary points on a curve and accurately determine their nature, whether they are a maximum or a minimum. Our learning objectives are: first, find stationary points using dy by dx equals 0. Second, determine the nature of these points using three methods. And third, apply this to sketching cubic graphs. In IGCSE mathematics, a stationary point, often called a turning point, occurs where the gradient of the curve is exactly 0. Imagine walking along a hill, at the very peak or the very bottom of the valley. For just a split second, you are walking on flat ground. Mathematically, to find these points, we take the derivative of the function, set it equal to 0, and solve for x. Let's see how this works in practice. Let's work through a typical IGCSE exam-style example to see this in action. Our first step is to find the derivative, dy by dx. Using the power rule, we bring the power down and subtract 1. To find the stationary points, we set this derivative to 0, because the gradient is flat at those locations. We can solve this by factorizing. Notice that 3x is a common factor. This gives us two solutions for x. Either 3x equals 0, which means x equals 0, or x minus 2 equals 0, which means x equals 2. Now, don't forget that a point needs a y-coordinate. We must substitute these x values back into the original equation, not the derivative. For x equals 0, y equals 0 cubed minus 3 times 0 squared plus 4, which equals 4. For x equals 2, y equals 2 cubed minus 3 times 2 squared, plus 4, which equals 8 minus 12 plus 4, resulting in 0. So, our stationary points are at 0, 4 and 2, 0. We have found the locations, but we don't yet know what type of points they are. Once we have found our stationary points, we need to determine their nature. This means deciding if they are a maximum, a minimum, or occasionally a point of inflection. The first method is looking at the gradient on either side of the point. Let's look at our point where x equals 0. We pick a value slightly to the left, like negative 0.1, and one slightly to the right, like 0.1. We plug these into our gradient function, which was 3x squared minus 6x. At x equals negative 0.1, the derivative is 0.03 plus 0.6, giving 0.63, which is positive. At x equals 0.1, we get 0.03 minus 0.6, which is negative 0.57, a negative value. Notice the pattern. The gradient goes from positive to 0 to negative. This forms the shape of a hill, meaning the point 0, 4 is a local maximum. Now, let's check x equals 2 by picking 1.9 and 2.1. At x equals 1.9, the gradient is negative 0.57. At x equals 2.1, the gradient is positive 0.63. The gradient goes from negative to 0 to positive. This forms a valley, meaning the point 2, 0 is a local minimum. This method is foolproof, but can be time-consuming with all that arithmetic. A much faster and more common method in IGCSE exams is using the second derivative, written as d2y by dx squared. The second derivative measures the rate of change of the gradient. In simpler terms, it tells us about the curviness or concavity of the graph. We start with our first derivative, 3x squared minus 6x. Then we differentiate again to get 6x minus 6. Now, we substitute our x values into this new expression. At x equals 0, d2y by dx squared equals 6 times 0 minus 6, which is negative 6. If the second derivative is negative, it means the gradient is decreasing. This occurs at a maximum point. Think, negative is a frown which looks like a maximum. At x equals 2, d2y by dx squared equals 6 times 2 minus 6, which simplifies to 6. If the second derivative is positive, it means the gradient is increasing. This occurs at a minimum point. Think, positive is a smile, which looks like a minimum. This method is much quicker than checking points on either side, provided the second derivative isn't 0 itself. If it is 0, you must revert to checking the gradients on either side. Now, let's connect this to sketching cubic graphs. Often, an IGCSE question will give you a factorized expression and ask you to sketch it, showing all key points. First, we find the roots or x-intercepts by setting y to 0. The solutions are x equals 0, x equals 3, and x equals negative 1. These are where the graph crosses the x-axis. Let's mark these points on our axes. Next, to find where the turns happen, we need to differentiate. It is much easier to expand the brackets first. Now, we differentiate to find the stationary points. We set this to 0. Since this doesn't factorize easily, we can use the quadratic formula. This simplifies to 4 plus or minus the square root of 52, all divided by 6. This gives x approximately equal to 1.87 and negative 0.54. Looking at our roots, x equals negative 0.54 must be the peak or maximum between negative 1 and 0. X equals 1.87 must be the valley or minimum between 0 and 3. To sketch, first, plot the roots. Second, identify the shape. Since it is a positive x cubed, it starts bottom left and ends top right. Finally, mark the stationary points calculated from our derivative. We can then draw a perfectly accurate sketch of the cubic function. By combining our knowledge of roots and stationary points, we can draw a perfectly accurate sketch of a cubic function. To wrap up, let's review the core skills we have covered today. You can now confidently find stationary points and determine their nature using multiple techniques. First, we use the first derivative by setting dy by dx to 0 to find the x-coordinates. Then, for the nature, method A involves inspecting gradients on either side of the point, or method B, which is using the second derivative where positive means a minimum and negative means a maximum. Finally, sketching involves combining roots and stationary points for accurate cubic graphs. In your IGCSE exam, always read the question carefully to see if it specifies a method. If it doesn't, the second derivative is usually your fastest route. Here is a final check of what a complete cubic graph looks like, with all its key features labeled. Let's do one final check. If you find a stationary point and the second derivative is positive, what does that tell you? That's right. It's a minimum because the curve is smiling upwards. Take a moment to practice these steps with a few past paper questions. The more you differentiate, the more instinctive these steps will become. Good luck with your revision.